Okay, so we define a geometric sequence is when we have a ratio, right, a common multiplier of successive terms is always the same non-zero number. Okay, so of course multiplying by 0 is just a bunch of zeros. That's a ridiculous sequence. That could be anything. Okay, but it's multiplied by or found by simply multiplying every previous term times a number. Okay, so remember from our discussion that this a sub n minus 1, right, this subscript refers to your previous term in your sequence. Okay, so we have the nth term, the next one after that is the n plus first term, and the one before it is the n minus first term. Okay, so if you're talking about n plus 1, that's after the term, and if you're talking about n minus 1, those are the preceding or the previous terms. Okay, so every term is found by multiplying the one before it times a certain number. Like in our first example. 2 becomes 6, becomes 18, becomes 54, becomes 162. Okay, so clearly these aren't adders, right? So if 2 plus 4 is 6, 6 plus 12 is 18, 18 plus something not the same is 54, right? So this is definitely not an arithmetic sequence because there's not a common adder. But do you see a common multiplier? Sure, 2 times 3 is 6. 6 times 3 is 18. 18 times 3 is 54. 54 times 3 is 162. Okay, so the answer would be yes, this sequence is in fact geometric. With a common ratio of, I believe, 3. Okay, so the ratio is when you take any term and divide it by its previous term. So 54 divided by 18. Sure enough, that's 3. Or 18 divided by 6. Okay, those are previous terms. Or 6 divided by 2. But all of these divisions, all of these ratios, when you divide the next term by the first term, gives you that same ratio, that same common multiplier. Okay, so remember, a ratio is just a comparison of two numbers. Okay, and if they always reduce to the same thing, then you have yourself a geometric sequence. So there's a formula for this also, right here. Okay, so we need to know the first term in order to write the equation, the first term, and the common ratio. Okay, so if we know the first term and the ratio, then we write our formula like that, always to the n minus first power. Okay, so that is our explicit formula to write the nth term, or the equation to generate any term of a geometric sequence. So let's see if we can use that for this next question. Write the first 5 terms of the geometric sequence whose first term is 3 and whose common ratio is 2. Okay, so the first term we are told is 3. Check. The second term we find by multiplying the first term by 2. So 3 times 2 is 6. And the third term we'd find by multiplying the second term by 2. 6 times 2 is 12. The fourth term, we multiply that one times 2. And the fifth term, we multiply that one by 2. And the sixth term, we multiply that one by 2. And so on and so forth. Okay, so if we wanted to use a formula, that would look like 3 is the first term times 2 to the n minus first power. Okay, remember this is an exponential, right? This right here is an exponential. So we don't ever multiply the 3 times the 2. It's not the same thing as 6. Okay, we always have a first term and our ratio. Okay, you have to have 2 parts. Now if you're missing a part, that means your ratio is the number and the first term is 1. Okay, because 1 times anything doesn't have to ever be written. So let's use this to find some stuff, like this one. What is the 9th term of this sequence? Okay, the 9th term. So we need to have a formula. Well, we know the first term is 10, but what is our ratio? Okay, remember, to find the ratio, we take any second term and divide it by the first term. So 9 over 10 is the ratio. It could have been done the same if you took 81 over 10 and divided by 9. You would have gotten the same ratio, but it's a lot more difficult than just doing 9 divided by 10. Okay, so if we want the 9th term, that's a sub 9. A sub 9 is equal to 10 times 9 over 10 to the 9 minus 1 power. Okay, so that's how we start, by writing down the formula, right? Plugging in our first term and your n value. So now we can do a little bit of simplifying maybe before we put this into our calculator. I know that 9 minus 1 is 8, so I can write that like this, okay, to the 8th power. And now maybe I'll do some distributing. 9 to the 8th over 10 to the 8th. Okay? So if I have multiplying this by 10, then one of these 10s can cancel out with one of those 10s. And I am just going to be simplifying or plugging into my calculator 9 to the 8th and 10 to the 7th. Okay, so hang on a second while I find my calculator, because I don't know what 9 to the 8th is in my head. Okay, that's what my calculator gives me. 43 point something million over 10 million. Okay, now maybe your calculator gave you a decimal, something like 4.3046 or 4.305. That would be the decimal equivalent of this ratio. But usually when it comes to geometric sequences, they're going to give it to you as a ratio, right? As a fraction rather than as a decimal. Okay, so just know, if you're looking at the answers in the back of your book or anything on your homework, that your answers will probably be written as fractions, not as decimals. Okay, so let's see what else do we have here. Find a formula for the nth term, so a formula, and then find the 7th term. Okay, so first let's start with the formula. We need 2 pieces of information. We need the first digit, the first term. That's pretty easy. Our first term is 3. And what is our ratio? So to find the ratio, we take the second term and divide it by the first term. So 36 divided by 3 is 12. Okay? So now I have all of my information to write the equation. 3 times 12 to the n minus first power. Remember, that's not 36, that's 3 times 12. So PEMDAS says first you do the exponents and then you do the multiplication. Okay, so you can't multiply before we exponentiate stuff. So if we want the 7th term, that means we're going to replace our n value with 7. 3 times 12 to the 7 minus 1. Okay, so this looks like a job for my calculator also, because I don't know what 12 to the 6th is off the top of my head. But my calculator does, thank goodness, and it tells me that the answer is that number, 2.985 million. Okay, now that's using the formula. Of course, if you wanted to, we could just multiply this one by 12, and then multiply that by 12, and then multiply that by 12, until you got the 7th number in the sequence, right? 1, 2, 3, 4, 5, 6, 7. Okay, but we wanted to use the formula so that we can practice using those powers of arithmetic and your PEMDAS, right? The way that we simplify these things. Okay, so now we have an algebra equation. The 4th term of a sequence is 125, and the 10th term is 125 over 64. what is the 14th term? Okay, so this is definitely an algebra problem that we can do a couple of different ways. Number one, we could find the ratio and the first term. That would be a good idea, because then we can use the formula to find the 14th term. Or you could do trial and error all the way around and see if you can figure this out. So I prefer the algebra method. So we have the fourth term, 1, 2, 3, 125. Right, that's the fourth term of some sequence that has a common multiplier. And then let's see, 5, 6, 7, 8, 9. 10th term is 125 over 64. Right? Sure enough. So then we want the 11, 12, 13. We want the 14th term. What is this term in our sequence? Okay. Well, there's the hard way and there's an easy way. So let's do it the easy way. Okay. Let's just imagine for a second. Let's use our imaginations. I know you're good at that. That our sequence actually starts here at 125. Okay. Let's imagine this for a second. That 125 is actually the first term of your sequence. Okay, times some ratio, right, to the n minus first power. So we're going to talk about that sequence for a second. So if that's our sequence, then that means 125 over 64 is the second, third, fourth, fifth, sixth, seventh term, right? So this is the seventh term of our imaginary sequence. So we know that 125 over 64 is the seventh term of our sequence. Okay, so we can replace our a sub n, right, with our term from the sequence, and we know that our n value is 7. Okay, so now we can figure out what our ratio is. Okay, and the ratio is going to be the same for our imaginary sequence as it is for our legitimate sequence, believe it or not. So we're going to solve this equation for r. Okay, so first step in solving this would be to divide by 125. Okay, so when I divide over here, rather than actually dividing, I'm going to multiply by the reciprocal. Okay, just because it looks better. And my brain likes to see this, because now I know I can simply cancel out those 125s. Okay, and cancel out this 125 also. So now I have 1 over 64 equals r to the 6th power. Okay, now this is an algebra equation I can solve by taking the 6th root of r. Right, that's how you get rid of that 6 up there, is by rooting it, which means I also have to 6th root this side. So this might be a little tricky for your brain. What numbers multiplies by itself 6 times in order to make 64?
2.
And believe it or not, that number is 2. Okay, so of course, the 6th root of 1 is just 1, because 1 times itself, however many times you want to do it, is always 1. But 2 times itself 6 times gives you 64. So we have just found our ratio. The ratio of this sequence is 1/2. So every number is half of what the previous number was. So let's see if that makes sense in our problem. So if this is 125, our next number is 125 divided by 2. And then 125 divided by 4. And then 125 divided by 8, I believe. And then 125 divided by 16. Okay, because we keep on multiplying the denominator by 2, which makes it 1/2. So yes, that does in fact work out to give me a 7th term of 125 over 64. Okay, so let's continue on doing that rather than using the formula. So I'm going to continue to multiply my denominator by 2, which is how we divide this, right? Multiplying by 1/2. So that's over 128. And then this is over 256. And then this is over 512. So our answer to our problem is 125 over 1024. Okay, that is the ratio, or the 14th term of our original geometric sequence. Okay, and we could have got that same answer using the formula, right, that we could derive using our ratio. But anytime we have a geometric sequence, okay, there's always a common multiplier between the terms. And that common multiplier is called your ratio. And you find it by dividing the second term by the first term, and then doing the multiplication through every single problem all the way throughout until you're done. Sorry, one correction.
You said you were gonna post it, like.
Gotta multiply this by 3. This only 12 to the 6th. So this answer, to be completely correct, is
It's 8,957,952.
this is the actual
Yes.
answer when you multiply 12 to the 6th times 3. Thank you very much.